Okay, now we want to continue with the synthesis reactions of alcohols. We want to continue with the synthesis reactions of alcohols. The first one for today, we are saying that we can prepare alcohols from esters. We're saying esters are hydrolyzed by aqueous sodium hydroxide solution to generate alcohols. However, this is not usually done since esters are obtained from alcohol. So we always prefer to prepare alcohols, esters from alcohols and not vice versa. So what we are saying, for example, if you have an ester is of the form Ara, so we have RCOO. Then R prime, this is an ester, this is an ester. So we can have RCOO, R prime, in presence of, going to use sodium hydroxide. We have said we are using sodium hydroxide. So sodium hydroxide is a reverse. It's going to reverse this compound into an alcohol. Carboxylic acids, right? So we are going to have an alcohol. It shall be ROH. It is ROH. Then the carboxylic acid here shall react with sodium hydroxide and shall give us ROO and what? Na. ROO Na. So basically this is our prime. So we can get an alcohol from a carboxylic acid, from an ester, but this is not very much preferred. Why? Because ideally it is an ester that is supposed to be coming from an alcohol, because we know that if you have an ester, if you have an alcohol, R prime, and if you add a carboxylic acid, R prime COO, H is the carboxylic acid. What do you form? The RO will replace the H, forming R prime COO, then R, COO, then plus what? Plus H2O. So this reaction here is called esterification. And we'll look at it when we are looking at derivatives of carboxylic acids, esters being derivatives of carboxylic acids. And we shall say an ester can be formed from an alcohol and a carboxylic acid. So this is the most preferable reaction. That's why in most cases when we have an ester where you can change it to an alcohol, here we have to heat. This one is possible, but it is not always advisable. We don't always go for it. Next, we want to look at the Caldizaro reaction. And in the Caldizaro reaction, in this case, the aromatic aldehydes, without the alpha hydrogen atom, undergo self-reduction and oxidation if in presence of sodium hydroxide. What I was saying, if you have aromatic aldehydes such as this one, they do not have the alpha hydrogen. What is the alpha hydrogen? The alpha hydrogen is the hydrogen atom that is attached to, it is part of the alkyl group that is attached to the carbon with the functional group in that case. So in this case, there are no alpha hydrogen atoms. So such can be reduced and oxidized. Reduction and oxidation, simultaneous reduction and oxidation is called when you look at oxidation, then when you look at reduction, then when they happen at this, if they happen concurrently, then you say that is a redox reaction. But if the same compound undergoes oxidation and reduction, we say it has undergone disproportionation in reaction. So this one is going to be oxidized and reduced at the same time. So in presence of, we are saying in presence of what? Sodium hydroxide. So we're going to have oxidation leading to the formation of a carboxylic acid. But now with the derivative, since there is a sodium here, so it will be like this. That is sodium benzoate. Then that is the oxidation. Then the reduction will give us an alcohol, which is actually of this format. An aromatic alcohol, CH2OH. So when the aromatic aldehyde becomes a carboxylic acid, it has been oxidized, has undergone oxidation. When it undergoes reduction, it becomes a what? It becomes an alcohol. And this is an aromatic alcohol. Remember yesterday we said you can form alcohols from what we call the aldehydes. We also said you can even get them from ketones. We said aldehydes will give us primary alcohols, and ketones will give us secondary alcohols. And if you remember here, we were using what we call lithium aluminium tetrahydride in presence of dry wax, in presence of dry ether. So that is how we are reducing an aldehyde to an alcohol. But this one here, the Cannizzaro reaction is different. Why is it different? Because we are not using any reducing agent. We are not having any reducing agent. The compound undergoes self-reduction itself and actually oxidation. All you need is to make sure it is in a basic pH medium. In presence of sodium hydroxide, this benzaldehyde will be oxidized to sodium benzoate, and actually that alcohol, that aromatic alcohol. So these are some of the reactions that lead to formation of alcohols. I know there are many others. You can always look out for them in the textbooks. Now we want to continue still on the production of alcohol, but now we're zeroing down to ethanol. We are zeroing down to ethanol. And this ethanol, we want to see how we can produce it domestically. I know right from O level we have discussed extensively how we can produce ethanol. I think even in science, P7 science also emphasizes how you can produce ethanol from starch. So we use either starch or you can use sugar. Sugar in this case is representing sucrose, right? And you know any examples of foods that produce starch? You can have cassava, so you can get ethanol from cassava. You can use wheat, you can use sorghum, you can use sugar cane. I think sugar cane can give us the sucrose. There are many foods that which if you ferment, they can actually be converted to ethanol, but through a series of stages. And we are saying this is only possible with the availability of enzymes. That's why you see we have enzyme stase, maltase, and yeast, and aminoxidase. This one, in most cases, these enzymes are available in yeast, right? So we are beginning with our starch. This is our starch. 2 moles of starch. They are combined with n moles of water, and they give us maltose. This is maltose. So they are giving us maltose. That will be our first stage during the fermentation, right? So this maltose here, if it combined with more water, 1 mole of maltose combined with water, 1 mole, they are giving us glucose now. They are giving us what? They are giving us glucose. Now glucose is further broken down by enzyme kinase, and this is still glucose. Further broken down by enzyme kinase to ethanol and carbon dioxide gas. So a question can come. Describe the stages that occur during the fermentation processes leading to the formation of ethanol from starch. So you know what to do. We are talking about how we begin with starch. Starch on further hydrolysis in presence of enzyme diastase gives you maltose, right? And maltose, if you further hydrolyze maltose, now in presence of enzyme maltase, it gives you glucose. And the glucose can be broken down by enzymes like this to ethanol. And the carbon dioxide gas in that case is a byproduct. So I hope at this time we have been able to discuss extensively production of alcohol. This one is domestic preparation. Now let's look at some of the physical properties of alcohols. Let's look at some of the physical properties of alcohols. Now, we are going to begin with solubility. Of course, remember when we're talking about physical properties, we're talking about properties that are affected by temperature and pressure. Talking about those are the properties that we always talk about. Physical properties, they are always affected by physical conditions. Solubility, of course, we know solubility is affected by temperature, and we are saying that the lower alcohols, the lower members are soluble in water. For example, ethanol, we have grown up knowing that ethanol is miscible in water, right? If you see these villagers who prepare alcohol, right? Where you go where they do the distillation process from, you'll actually realize that after they have prepared that home solution of ethanol, they dilute it so that they can make a lot of profits from it. Even those of you who like drinking those waters, some of them, if they are not diluted, they might be dangerous to our body. So they are soluble in water. But that is, remember now, the ethanol which we use has two carbon atoms. By formula, it is CH3, CH2OH. So it is small. Even methanol is the same, soluble in water. Even propane, CH3, CH2, CH2OH, soluble in water. However, the moment we start increasing the number of carbon atoms to 4, butane might find it so hard to dissolve in water, right? And why is it that the solubility reduces with increasing molecular mass? This is because as we are increasing, for example, look at this CH3, CH2, 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 CH2OH. Look at such a compound. It has a very big group of the hydrocarbon. And hydrocarbons, remember we said, they are predominantly covalent and non-polar. So the only polarity here is between carbon and oxygen and hydrogen. Partially negative, partially positive. The only polarity is here. But the bigger part of the molecule is non-polar, right? So if the bigger part of the molecule is non-polar, it will reduce the polarity of the whole substance. That means the whole substance will be somehow non-polar. Remember, solubility is facilitated by what we call hydrogen bonds. Hydrogen bonds. Now, you may not know what hydrogen bonds are. I will just simply illustrate what hydrogen bonds are. For example, when you look at ethanol, if you have ethanol, that is CH3, CH2OH, right? Now I can have another CH3, CH2, then OH. So there is, if we have ethanol molecules in a solution, if we have ethanol molecules in a solution, these molecules are always bonded together since this is a covalent compound. The molecules in a covalent compound are bonded together by what we call van der Waals forces. Van der Waals forces of attraction. These forces are weak and they are present in covalent compounds, right? So since these are covalent compounds, they have van der Waals forces. But because of the OH group in the alcohol, they are what we call hydrogen bonds, the H bonds. That's why I've included the H bonds there. So the importance of the H bonds, or how they come into play, is that the oxygen from this molecule might be attracted to the hydrogen of the next molecule. So there might be a force of attraction between this oxygen and that, right? Then this hydrogen might be attracted to this oxygen. The hydrogen and the oxygen of different molecules in a compound, they establish that kind of polarity. Because remember, this one is always partially negative, this is partially positive. Partially negative, partially positive. So the moment they are close to each other, the unlike poles will create a force of attraction. The same will apply to this oxygen here might attract the hydrogen from the neighboring what? From the neighboring molecule of ethanol. Of course, in a solution of ethanol, there are many molecules of ethanol, right? Now, how does solubility come into play here? Now that we have understood what hydrogen bonds are, assume there are water molecules here. Of course, water molecules are in this format. So we have water molecules. That is HO2, right? So I expect if these are ethanol molecules, they are going to establish hydrogen bonds between themselves and the water molecule. This oxygen in ethanol would establish a connection with the hydrogen in water. The same applies to this oxygen in water might establish a connection with the hydrogen of that ethanol. So the moment there are forces of attraction between different molecules, the molecules of water are being attracted to the molecules of ethanol by hydrogen bonds. It means that if these hydrogen bonds are strong, then the solutions will mix uniformly. So what causes the solutions to mix uniformly are these hydrogen bonds. That's why when you mix them, you might not be able to separate them with your physical eyes. However, we are saying, as the molecule becomes big, what happens is that these hydrogen bonds start to weaken because the molecule is predominantly non-polar. Are we together? So if the molecule becomes big like this one now, this OH still might establish the hydrogen bond with what? With water. But this hydrogen bond will be so weak. Why? Because first of all, the number of hydrogen bonds are going to be few. And secondly, the compound is predominantly non-polar because the hydrocarbon part is big. And because the non-polar part is big, then the whole compound will be generally non-polar, we shall say it is less soluble. So the solubility decreases with increasing molecular mass because of the what? Of the increasing hydrocarbon part. The non-polar part is increasing, which reduces the strength of the hydrogen bonds. The strength of the hydrogen bonds. Now, also boiling points, of these alcohols are closely related to hydrogen bonds. Why? Because the hydrogen bonds are stronger than the van der Waals forces. If you have two covalent compounds, one has hydrogen bonds, the other one does not. The one with hydrogen bonds will have a higher boiling point because hydrogen bonds are stronger than the van der Waals forces. So if you are comparing, for example, CH3 molecules, CH3 molecules, these ones are bonded by van der Waals forces. However, if you are comparing CH3 OH, CH3OH molecules, these ones are bonded by hydrogen bonds because of the presence of the OH. Are we together? Because of the presence of the OH. The OH creates hydrogen bonds. Hydrogen bonds are basically formed the moment oxygen is bonded to a highly electronegative atom in that compound. The possibility of hydrogen bonds increases in such a sense. But remember, even the van der Waals forces are here because these are also covalent compounds. Therefore, this one has both van der Waals and hydrogen bonds. This one only has van der Waals forces. That means this compound will have stronger bonds which require a lot of energy to break. Therefore, this one will have a higher boiling point compared to this because this one only has van der Waals forces which can easily break. That's why this one occurs as a gas at room temperature, whereas this one is a liquid at room temperature. So that also shows you that the bonds here are weaker than the bonds here because the bonds in liquids are naturally stronger than the bonds in gases. Then the last part there, we have the density. We're saying that the density also increases with molecular mass. If the molecular mass increases, then the density will increase. The density will do what? Will increase. However, the branching now, when branching comes in, that will increase the density. What do I mean? For example, if I give you two compounds, you have CH3, then CH3, OH. That one I'm comparing it with CH3, CH2, CH2OH. All of them have 4 carbon atoms, right? But when you look at this one has a lot of branches. This one is a branched compound, whereas this one is not branched. This is primary alcohol, this one is tertiary. So this one will have a less density compared to this, right? The branching reduces the density in compounds. So if you have to compare these two, you find that whereas they have the same molecular mass, this one is less dense than this because of the branching. Also, we are saying aromatic alcohols are denser than aliphatic alcohols. Aromatic alcohols, they are the ones which have what? The benzene ring in their skeleton. The benzene ring in their skeleton. So these aromatic alcohols, where this R now is a methylene group, or methylene groups. So in this case, in most cases here, the benzene ring increases the density of the what? Of the compound. Why? Because the benzene has a benzene ring has a lot of atoms that are condensed on one piece. What I'm saying is, for example, when you look at this, if you have to compare it with CH2, CH2 6 times, you see that this one takes a lot of what? A lot of space. And the moment it takes a lot of space, it becomes lighter because density is to do with packing. If you are closely packed, then you are denser, right? If you are not closely packed like this one, you are spaced, then you are less dense. That's why aromatic alcohols are denser or heavier than the aliphatic